Okay, greetings from Utah. This will be our last lecture for the summer 2022 season. I don't know about you guys, but I'm a little bit exhausted and I'm kind of ready for this all to be done with. So, this is our last lecture, and the funny part about acids and bases, it's kind of the last thing you learn in chemistry, and so you're kind of done at that point, and it's something that you may or may not kind of internalize as well because you're just so full. So I'm going to get through a couple of things here. I'm going to get through the conversation around pH. And so, we've got all the bases now. We've got rates of reactions. We've got what an acid and base are. We've got Le Chatelier's principle and equilibrium. And so we're ready to sort of build all that up into one of the other ways we measure acids and bases, which is pH. And then we'll talk specifically about buffers there at the very end. So we're going to finish all of this here. And we'll do our final push here. So I appreciate you guys and your patience with this. I intended to get these done last week. So we're going to just rock and roll and get her done. So basically this statement at the top, acids and weak acids and bases exist in equilibrium. So you have to understand this concept of equilibrium where, you have this acid, right? And it's going to donate its hydrogen to the base. That's our definition of an acid and a base, a proton donor and proton acceptor. This concept of it being at equilibrium, that there is a forward reaction equivalent to a reverse reaction, and therefore there's all of these species in the solution. There's the this over here, the conjugate acid. So the conjugate acid being the leftover, whatever is the base, it's in partnership with this conjugate acid. So we have these conjugate acid base pairs. And then over here, the conjugate base. So in the reverse reaction, the hydrogen gets donated to that base and then it goes backwards. So hopefully that kind of makes sense. So we have this forward reaction of this acid and this base reacting. We have this reverse reaction of this acid and this base reacting. And they exist in this happy place of equilibrium. In the last video, we talked about Le Chatelier's principle. In fact, that you can actually disturb this equilibrium and you can cause the equilibrium to shift, which is also a big idea that we're going to talk about with buffers. So just kind of looking at an acid-base reaction, just kind of understanding that the acid donates to the base, right? And then you have a leftover base over here. So being able to kind of look at those reactions, understanding that the reason this is an acid is it produces the hydronium ion in solution. So all of those pieces hopefully are coming together. That the charge of the acid goes down. So we go from a neutral substance and we lose that proton. There's that positive and that negative. Okay. Putting that together with the equilibrium constant, if we write the equilibrium constant, we'll call this, because it's an acid, we're going to call it a Ka rather than the Kq. We're going to put the products over the reactants, and we're going to leave out the pure water because we said that concentration can't change. So we have the same sort of idea. We have this equilibrium constant that goes along with this weak equilibrium of an acid in this case. And what we understand is if there's more reactant, let me try that again. If there's more product here, this indicates that, this is kind of a stronger weak acid. So basically that's the reason for the K conversation in the last video is, if you have a large K, you've got more product than reactant. And if you have a small K, you have more reactant than product. And this just translates into the strength of an acid. And so we can actually measure the strength of these weak acids, which are in equilibrium, by their K values. So it's kind of like you have these weak acids, and in that category of weak acid, you have stronger weak acids and you have weaker weak acids. Okay. And so that is just this sort of hierarchy, I suppose you could have in this acid category. So this one is the stronger of the weak acids in this list, right? This is the acid that's going to donate its hydrogen more readily. And really, when you talk about the strength of an acid, it is literally how easily the hydrogen is donated away from that molecule. Okay, so there is how Ka shows up and in the classifying of weak acids in the category of a strong weak acid to a weak acid. And in that same vein, we kind of build the concept of pH in the same way. So we call water amphoteric, and I want you to think about the prefix amph, right? Amphibian, right? This is a species that lives in both the water and on the land, right? So it does both things. And we've kind of talked about the fact that water can sometimes act as an acid and sometimes it can act as a base. And so I want you to think about that. So if we say this species right here of the water in our situation is an acid and this one is a base, that would imply that the acid is going to donate its hydrogen to the base, and we'd have OH left over from the acid, and we'd have H3O plus. Whoops, I want to do that in a color. H3O plus in as a leftover from this. And so we again have this acid base pair, right? So we've got over here, we've got the conjugate base. And over here, we have the conjugate acid. For the reverse reaction. So this is interesting that in water, you have this equilibrium. And in any sample of water, you're going to have a little bit of base and you're going to have a little bit of acid, which is interesting. But the point is there's not very much, and I'll get to that in just a second. So again, if we write the equilibrium expression, we want to know, we're going to call it Kw. So we had Ka when we dealt with acids, we have Kw when we deal with water. We write the products over the reactants, and it turns out that we don't include the water in that. So we have this equilibrium expression that doesn't have a denominator. It just has a numerator. Well, it turns out when we write that Kw expression, by lots and lots of research for a long, long time, they find out that in any sample of water, this concentration is 1 × 10 to the -7th molar. That's moles per liter. So there's very, very little OH present. And this, and this number right here is also the same. 1 × 10 to the -7th molar. So long story short is, in any sample of water, neutral water, we're going to have equivalent. So the OH concentration is going to be very small, A, and B, it's going to be equal to the H3O plus concentration, also very small, but basically that's what makes it neutral. I keep erasing what I'm trying to write here. That's what makes it neutral. The fact that these are equivalent means that this is a neutral situation, and that's kind of where the basis of the pH scale comes from, okay? So a couple of things, I was fascinated by this when I learned it. This 7, right, is where the neutral pH comes from, and I'll get to that on the next page. pH is equal to 7. When I multiply those two numbers together, my Kw is a constant, 1 × 10 to the -14th. And if you have any familiarity at all with pH scale, you know it goes to 14. So that is kind of the basis for why we have a pH scale that goes from 1 to 14. So that's kind of what this says. The Kw is 1. The exponent on this is giving us the basis. This is the base for the pH scale. So we have a pH scale, we have 1 to 14, and the pH scale, it turns out, is a measurement of the hydrogen ion concentration. And so I just have a little tiny lesson right here where I want you to kind of not get so intimidated by this log. Everybody gets all weirded out and it's the end of the quarter and they get freaked out, but this basically is, there's 2 formulas that we deal with when we deal with the pH scale. And this log is what freaks everybody out. So I'm going to try to assuage that fear for just a moment. So bear with me while I try to talk about this, right? So if you think about logs, really all it is an inverse function. And you're very familiar with inverse functions. Because you know that if I want to solve an equation to get to a value for an x variable that is added to something, you very well know that you subtract it because the inverse of addition is subtraction, and that would get us our variable x. If I had our variable multiplied by 2, I would know that the inverse of multiplication is division, and so I would divide by 2. So you are very familiar with inverse functions. The inverse of addition is subtraction. the inverse of multiplication is division. The inverse of a squared term, right, is the square root. And so we have these inverse functions that we use all the time, and they're very familiar because you've worked with them a lot. You may or may not have dealt with a variable exponent, right? So if we want to get to this exponent right here, we have to use the inverse of the exponent. And so when we think about an exponent that is a variable, we have to have a function that undoes it, and that function is a log function. And that's all it is. It freaks students out, but really the only job that a log does is undo the exponent. So logs, they undo exponents that are variables, okay? So that's kind of where this pH scale comes from. It says right here, the pH scale, if I can get to the highlighter, the pH scale is directly related to the hydronium ion concentration. Often you'll hear them say H plus, or the hydrogen ion concentration. And essentially when I have a 1 pH, that means I have a high H plus concentration. And when I have something down here on the 14, I have a low H plus concentration. And when I'm in the middle, I have H plus concentration equal to OH minus concentration, and that's what makes it neutral. So as I go this way, I get more H plus, which makes it acidic. And then when I go this way, I have less H plus, which makes it what we're going to call basic. Okay, because as the H plus concentration goes down, the OH minus concentration goes up, because these guys are inversely related. So I've got my OH concentration, I've got my H3O plus concentration, and they are related to each other by a constant. And so this again is an inverse relationship. As this goes up, this is going to go down in order for this to stay the same. And it's a combination of fatigue at the end of the quarter, the log idea, and these negative exponents that make this a hard concept for students to gather. And so I'm going to try to kind of assuage that fear. Okay, so let's talk about that for a second. If I have a neutral solution, I know that the H3O plus concentration is equal to the OH minus concentration, and that the pH is equal to 7. And that basically means that the OH concentration is 1 times 10 to the negative 7th molar, and the H3O plus concentration is 1 times 10 to the negative 7th molar. Okay, so these guys at a neutral solution, and you saw this in the lab, usually it was green with a universal indicator, right? And you know, some people have like alkaline water. There is a whole movement of water being alkaline, and they think it's better for the body. But in most cases, the water that we're drinking is going to be neutral. Okay, if we have an acidic situation, basically what we mean in that solution is there's going to be more H3O plus. That's basically what that means. And this is kind of counterintuitive, but basically I'm going to make this pink because usually you saw that the acidic solutions are kind of down here. They're pink and they're red, right? So the acidic end, basically the pH is less than 7. So the low numbers give us high H3O plus concentration, and I'll try to explain that in a minute. So this means that the OH minus concentration is going to be less than 1 times 10 to the negative 7th, because it's going to go down, right, as the H3O plus concentration goes up. And this is going to be more than 1 times 10 to the negative 7th, because if you get acidic, the H3O plus concentration is going up. Now that's counterintuitive because of that negative exponent, but I'll try to explain that in just a second. This one, basically, again, we're focusing on the H3O plus, so we're going to say this has less H3O plus. And you could translate that to say more OH minus. And you could translate this to say less OH minus. In this case, we're dealing with these substances down here, and generally they're blue or purple as you saw in the demos, right? And so this is where the pH is greater than 7. So we're dealing with the high end of the spectrum, right? And so this is going to be where the OH concentration is more. So this just flips. So that's more than 1 times 10 to the negative 7th, and this is less than 1 times 10 to the negative 7th. Because again, if we rewrite that KW expression, that equilibrium constant, which is basically, you know, the sort of third formula that we need when we're dealing with pH, is we know this is always a constant. So as this goes up, this has to go down. And conversely, as the OH concentration goes down, the H2O plus concentration goes up. So this is where we have acidic solutions, and this is where we have basic solutions. More OH, right? More OH means basic. Let's do this in pink. More H2O plus means acidic. And so that's kind of the name of the game. And again, students freak out about this, but it's really, if you kind of go with it in terms of the log just being an undoing of the exponent, then it shouldn't be too bad. Okay, so let's look at how those problems would look. So basically, you have 3 formulas that you're going to deal with when you're doing pH problems or acidic basics problems. There's this one, right? Those 2, and then this one right here. So what I want to do is pH is when you're given the H2O plus concentration and you want to find the pH. That's when this one's going to be used. And for this next one, if you're given the pH and you want to find the H2O plus concentration, that's when this one's going to be used. And then the third one is, well, you've got this constant and you're going to be given one of these, and so you're supposed to find the second one. So you have this formula that has 3 variables in it, and you're going to be given 2, and you're supposed to find the third. So these guys all work in tandem with one another. Okay, so here's how it goes. So basically, again, you know, often these are multiple choice questions, and it's not too bad because you can just kind of look at the exponent and know what the answer is. Okay, with a little exception because of the coefficient. So let's just start in. So it says calculate the OH concentration. I should put that in blue. Let's try that again. Sorry, my parents have a clock in my dad's office. Okay, so we want to count it. It's 10 o'clock, so we're going to get 10. It's nice to take a little pause. Okay, so this question says calculate the OH concentration when we're given the H2O plus. Okay, so basically what that implies is these numbers right here, this is the H2O plus concentration as 10 to the negative 8th molar. So I don't know that I mentioned this before, but when we do these brackets right here, that just implies concentration and molarity. So we don't even have to do much here. Basically, all we really need to do in this case is go, okay, well, if we're going to take, we're given our formulas are pH is equal to the negative log of the H2O plus concentration. H2O plus concentration is equal to 10 to the negative pH. And then our third one is KW is equal to OH minus times H3O plus. So essentially this one, we would plug this in and we'd say, well, we want to know the pH, and that's the negative log of 10 to the negative 8th, which is also 1 times 10 to the negative 8th. I just want you guys to recognize that. Okay, this is a simplified version. We just kind of simplified it. So ultimately, we can look at this and know the answer. This negative is going to undo the exponent because we have small amounts of concentration, so the values are going to be very small. That's why the negative exponent. The log undoes this exponent, and so basically, long story short, we can just look at this and go, yeah, the pH is 8. Yeah, the pH is 8. And so the question is this acidic or basic? And because our scale goes 1 to 7 to 14, we know this end is acidic, and we know this end is basic. Because the 8 fits right here, we know this is a basic solution. So that's as bad as it gets, kind of, right? So so you can basically look at these values right here and go, yeah, because this is 8, this is going to be basic. Because this is 10, this is going to be acidic. So that, without the coefficient, you can just look at the exponent on the H3O plus concentration and you can go right to the pH. So that kind of takes even the formula away. It takes that scary formula away. Now, when you have a coefficient like this, it makes it a little bit different. It's not quite as cut and dry, but it's very, very close. And so here's my ask. In this one, if you just look at the exponent, you can estimate that the pH is going to be, guess what? Around 4. It's not going to be exactly 4 because of this coefficient, but it's going to be somewhere around 4, and you can answer that question. Oh, that's acidic, right? On this one, again, just cheating. It's not going to be exactly 11, but it's going to be approximately. The pH is going to be approximately 11, which makes this basic, right? It's not going to be exact. And so let's figure out the exact. Okay, so if we want the pH, we're going to calculate negative log of 3 times 10 to the negative 4th. And I'm going to try to go here for a second. I want my calculator, and I'm going to try to do this for you so you could see it. Where is my calculator? Right there. And then if I can get the log. So I'm not sure how to do this, and I will want to make sure this is right for you. So hold on a second. What did I just do? I did something weird. I don't want history. Okay, go away history. How do you go away? Okay, so what we want to do is we want to put 3.0. We're going to do times 10 to the, what was it? Negative, oh shoot, I have to go back to our notes because I have such a short attention span. To the negative 4th. Okay, back we go. So we're putting in our exponent of negative 4. And then we're going to take the log of that. Goodness me. So we're going to take the log of that. And I think I did that wrong. So I'm going to clear it out. So the log base 10 of 3 exponent to the negative 4th equals. Okay, so there it is. And then I'm going to take the log of that. Okay, I didn't take the negative log of that. So, okay, one more time. Clear, clear, clear. Okay, so I'm putting in my value, 3 times 10 to the negative 4th, right, equals, and I got a value, so that number should make sense. And I'm going to take the negative log of that number, and it doesn't like that. That's totally fine. I'm embarrassing myself on the last day of class, just like on the first day of class. So that's okay. So there's our number. I'm just going to take the log of it, and there I get my answer. So 3.5. So I'm going back to our notes. And so I'm having syntax errors, but if I do negative 3.5, I get 3.5. So here's my point in this conversation is we said we know that by looking at this value, the pH is going to be somewhere around 4. This number right here makes it not exactly 4, but this is close enough. And it gets us to a place where we understand that the pH of this system is going to be acidic because it's down here in this range. And so if you had that universal indicator in there, it would be kind of yellow, pink, red in that area to be acidic. Okay, I'm not sure how I did with the calculator, but hopefully I made that clear. And the same thing would happen right here. We know this is going to be about 11, but not 11 because of the coefficient. So hopefully that makes sense. Okay, so let's talk about this question right here. If I have a urine sample and its pH is 5.9, we want to calculate the two concentrations. Okay, a couple of things. First of all, with a pH of 5.9, right away we know this is acidic, and you might know that about urine already. So this is an example of when we're going to use the second equation. We're going to use the second equation because this time we're given the pH and we want to find the hydrogen ion concentration. So we know right now, just looking at this, that when we do this, we're going to have a number times 10, and this exponent is going to be somewhere, it's going to be somewhere around negative 5.9. Okay, we already know that based on just the pH because that's how this works, and you can kind of maybe already anticipate that just a little bit. So when I do this, and I'm going to go embarrass myself with my calculator again, I'm going to raise 10 to the negative 5.9 to get the hydrogen ion concentration. So going back to my calculator, I'm turning it sideways so we can use all of it. I'm going to clear it, and I'm going to raise 10 to the power of negative 5.9. Okay, so there's my value. I'm going to kind of note that. So that says 1.26. 1, 2, 3, 4, 5, 6. 1.26 times 10 to the negative 6. Okay, so I'm writing that down into our notes. 1.26 times 10 to the negative 6th molar. Okay, so what did I just do? Well, I'm asked to find the hydrogen ion concentration based on the pH. So I used the formula that helps me get there. I just figured out that the concentration of the H3O plus is 1.26 times 10 to the negative 6th. My point is this number is really close to this one, but not exact because I have a coefficient. Okay. So the next piece of this equation, the next ask on this question is to find the OH concentration. And that's where we have to go back to this formula right here. So we know it's a constant, 1 times 10 to the negative 14th. We know our H3O plus concentration, so we're looking for the OH minus concentration, 1.26 times 10 to the negative 6th molar. The big point here is without even doing any calculation, because this is negative 6 and this is negative 14, if you're familiar with what happens with exponents when you multiply them, exponents add together. So if I have negative 6 plus negative 8, I get negative 14. And so basically I can already anticipate that this exponent right here is going to be somewhere close to negative 8. Okay, I already know that. And so I could kind of like, if I had a multiple choice question, I could maybe look at that and already figure that out without even doing any math. Now here's the hard part. Again, I'm going to embarrass myself on the calculator. But what we want to do is we have to solve this equation for x, right? And so in order to do that, 1 times 10 to the negative 14th is equal to the OH minus concentration times 1.26 times 10 to the negative 6th. We have to do the algebra. We have to divide both sides by this to get to this, okay? So when we do that, we have to put that in the calculator. And so again, I'm going to try to embarrass myself. We'll see if I can do it. So we're going to do 10 raised to the negative 14th, and we're going to divide that by 1.26 exponent to the negative 6th, and hopefully this works. Okay, so again, it doesn't spit it out very nicely on this calculator, but hopefully you have a better one. But I'm counting zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 7.9 times 10 to the negative 9th. So I get 7.9 times 10 to the negative 9th. Now, what I said in the previous picture here is we know that this exponent is going to be somewhere around negative 8. It turns out that we got negative 9, but again, that's because of this coefficient. What I'm going to try to show you here is if you were to check this, I'm putting this back into the original equation. Kw is equal to OH and H3O plus multiplied together. If I put in that, the calculation we just figured out, 7.9 times 10 to the negative 9th, and I multiply it by 1.26 times 10 to the negative 6th. When I multiply these two numbers together, I should get something close. Okay, and you can try that to prove it to yourself. The other thing I want you to notice is those two numbers should add up to approximately negative 14. And the reason I say that is because students freak out and they can't quite make their calculators go, and they get exponents like negative 22 or something like that, and that just means that they aren't using their device, their instrument, very correctly. So those exponents are always going to approximately add, they're approximately going to add approximately to negative 14, and that's a way to check it. Another thing I want you to mention and I want you to pay attention to is we said the pH of this urine is 5.9. Well, that would indicate that this concentration of the H3O plus, right, is higher than the concentration of the OH minus. And so we corroborate that by just looking at the exponents. This concentration, even though this is a smaller number, -6, is closer to the number line, or to the 0 on the number line. That number is bigger, right? This number is smaller, and so that corroborates that this would be an acidic solution. More H3O plus than OH. Okay, so there's lots of ways you can go through and you can check to make sure you're doing these questions correctly. And again, you know, it's very, very scary for students, but it's not too bad. 3 formulas that work together depending on what you're being asked for. And I know John has lots of practice for you guys to do. Okay, last but not least, we want to talk about buffers. And you saw the video that Scott did for us, which is probably the best way to talk about buffers. But basically, a buffer is a solution whose pH changes very little. And that's the whole idea. We want to have a solution that can absorb any acid that goes in, and we want to have a solution that can absorb any base that goes in. And when you watched the video, you saw that when he added acid or base to water, instantly the pH changed in accordance with that scale. Bluer for base and redder for acid. When acid or base is added, okay, so a buffer is a solution whose pH changes very little when acid or base is added. A buffer is a solution composed of approximately equal amounts, and it has to be a weak acid. And the reason it has to be a weak acid is because the acid has to be in equilibrium. That is the reason. A strong acid, right, when it reacts, it completely ionizes, and I don't have anything on this side of the equation to absorb anything because it's all over here. So we have to have a weak acid in order for that to be a buffer. We also build this weak acid base system with a conjugate base. Okay, so what that means is we're going to build that equilibrium. We're going to build the equilibrium with a little bit of acid and a little bit of base, and it's kind of like we build the equilibrium from both sides. We have those both present in the solution. The buffer resists change in pH when the added base reacts with the weak acid and the added acid reacts with the conjugate base. And so you have this solution has the ability to absorb certain acid if you add it, or base. And this is kind of what's going on in the blood, right? So when we ask the question down here, right, why do we have to have both the weak acid and the bases? We've got to have the acid present to absorb the base, and we've got to have the base present to absorb the acid. And all of this goes back to Le Chatelier's principle. Okay, so here are our questions. What happens to the concentrations of the acid and the base when a small amount of acid is added? So if we look at that from this point of view, so here is the sort of base equilibrium. So this is kind of like from the point of view of the base absorbing the acid. Here's kind of what's going on. So NH2 minus plus H3O plus. I don't know why my pencil is not working very well. It's probably not charged. So what happens here? Well, if I add acid, right, that's going to react with the NO2, and basically what's going to happen is this equilibrium is going to, because I'm removing this, I'm taking it out, the equilibrium is going to shift, and this concentration will go down, and this concentration is going to go up. This concentration will go down because we're shifting the equilibrium, reacting that so that this can go the other way. I think my pencil must be, it says it's 100%. It must be the operator this morning. And then what happens to the concentrations of the NO3 and the NO3 when the base is added to the buffer? So basically here is what we're looking at, right? If we add base, that's going to decrease the concentration of the HNO3, and again, the equilibrium is going to shift. So that one's going to go up and this one's going to go down. And so again, just this sort of explanation of an acid-base system, the buffer system, is you've got a little bit of acid in the solution to absorb the base that's added, you've got a little bit of base in the system to absorb the acid that's added. And that keeps the pH constant. And you saw that very, very visually in the demo that Scott did. Now, I guess my last part here is how do we make, how do we identify whether we have an acid or a base that works to make a buffer, because not everything does. So we have to have two criteria. We want a weak acid and we want its conjugate base. And that's why we had to use that word earlier. Because this is a strong acid, that cuts it out right away. The HCl is a strong acid, so that kind of cuts this out. But I did want to mention that KCl is the conjugate base. Because when KCl goes in solution, I'm sorry, you guys, I get K plus and Cl, and that is the conjugate base. So we have, this is a conjugate base, but that is not a weak acid, so this does not work, right? When I look at this right here, you might not know that it's a weak acid, but you go back to our little chart of weak acids right here, and there's the carbonic acid right there. Carbonic acid is a weak acid, so that meets the first criteria. So that, so far so good. We've got a weak acid, so good. NaHCO3, is that the conjugate base? Well, thinking about how NaHCO3 falls apart in solution, we get Na plus and HCO3 minus. This right here is what would be left over if we lost one hydrogen. And so yes, this corroborates that is a weak acid and a weak and its conjugate base. So we've got both criteria. So this is a good source of a buffer. Okay. Keep going down this list. The other thing here is these guys, this is definitely a weak acid. Again, I don't know that for sure unless I go back to the chart. H3PO4, phosphoric acid. So that meets the first criteria. That is a weak acid. But the conjugate of this acid, H3O-PO4, would be H plus and H2PO4 minus. And that has nothing to do with it. So this is a weak acid. That meets the first criteria. And that is not its conjugate, so that won't work. So you got to have the leftover, that conjugate base. Once one hydrogen's given away, what's left over, that's the conjugate base that you want. And the weird thing about it is it's never going to come all alone. It's going to come with a spectator ion that's in there. And Scott mentioned that also in the demo. Okay, last, and I think, hopefully this makes sense. This right here is a weak acid. This is acetic acid. Again, looking it up on the chart. Acetic acid is right there. Different formula, same thing, right? CH3COOH, there it is. And this is just going to put the hydrogen out front. And then KC2H3O2. So what you're seeing there is you're seeing C2H3O2, C2H3O2, and there's your spectator ion. So this is a good candidate for because it has both. So there's two opportunities to have a buffer system here. Again, has to have a weak acid and its conjugate base. Okay, you guys, I know it's hard at the end because pH and logs and blah, 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 so much stuff here. It always gets kind of squishy in the summer session. So I appreciate your attention. I appreciate your effort this quarter. I know we're all very tired and looking forward to a good break. So thank you. Have a great day.